This video will cover processing date and time data in dplyr. The code used in this video is available on the Learning Management System. We'll use the data file hourlyweather2017.rds. You should download both of them now if you'd like to follow along. By the end of this video, you should understand how to process date and time data using dplyr, and you'll learn some useful lubridate functions for summarizing date and time data. So far, all the lubridate examples have just operated on single values inside variables, but all of the lubridate functions integrate into dplyr workflows the same as other R functions. So for example, if you had a text date in your data, you could convert that to a lubridate date using something like the ymd_hm function inside of a mutate verb. We'll work through some examples of processing date and time data in dplyr. First, let's load some setup code, including a data file. Just to remind you of the content of that file, let's glimpse it. You can see the weather data table has a year, month, and day variable, an hour variable, the temperature in degrees Celsius, and the relative humidity. The first thing you might want to do is create a date variable from those date components, the year, the month, and the day. These are separate numbers. If you'd like to convert them into a piece of text representing the date, which lubridate could then later process, you can use the string C function to smash those components together using the hyphen as a separator. Running that code, it adds an additional column to my weather table. We can take a look at it with glimpse. And you can see there is now a new field, date.text. It's the character data type, so this is just text. It contains the year, followed by the month, followed by the day, separated by hyphens. Going back to my code, remember this is a textual representation of the date. To convert it into a lubridate date, we can use the ymd function. The text is ordered year, month, and day. I'll create a new variable called date, containing the lubridate version, and then we'll take a look at it in the output window. You can now see that there is a new variable named date. The data type is date, and it contains those textual date values now in the lubridate date format. Going back to my code, this data file is actually hourly data, so you might, instead of a date, like to create a date time. You can do that using the same kind of workflow. First, I'll create a variable datetime.text, smashing the date text together with the hour and separating them with a space. Then I'll use the ymdh function to convert that piece of text into a lubridate date time. And the last little bit of code I have there, I'll just select the variables that I'm interested in, which is the date time text, the date time, the temperature, and the relative humidity, and we'll take a look at the output. You now see I have a new tibble with date time text, the date time value as a lubridate date time, the data type dttm, followed by the temperature and the relative humidity. Going back to my code, an important consideration when dealing with date time data is setting the time zone, getting the time zone correct. These are weather data from College Park, which is in the America/New York time zone. So what I'm going to do is take my weather data, I'll pipe it to the mutate verb, we're going to reconstruct the date time from the date time text. I'll make that variable date time equal to the ymdh function. I'll provide the date time text, and then I'll explicitly set the time zone using the TZ option to America/New York. I'll run that code. Then I'll print out the first several rows of data. You can see there is now a date time column. The values still match the date time text, but now they're encoded in the America/New York time zone. This doesn't print out in the print mode, but that information is encoded in the tibble. Let's go back and look at my code. How could we check to make sure this is in the America/New York time zone? To do that, you can use the with_tz function. Remember, this takes a date time and changes the time zone, but keeps the moment the same. So here I'm going to take that date time and re-represent it in the UTC time zone. Let's run that code and look at the output. Now you can see there is a new column, datetime.utc, and for the values that we see here, you see it's 5 hours ahead of the original date time value, which is in the America/New York time zone. Constructing date times aren't the only component of date and time data that might show up in your workflow. Frequently you want to summarize data. For example, compute averages over long periods of time, say weeks, months, or years. To do this, you might actually want to round off dates and times. LubriDate provides several functions for rounding dates and times. The three important ones are round_date, floor_date, and ceiling_date. These functions each take two arguments. The first is a date time, and the second is a unit in quotation marks. So for example, the round_date function would take a date time, and if you want to round to the nearest month, you would put month in quotation marks. How do these functions work? They're going to convert dates and times to even values. What is an even value of a date or a time? It's the moment a new calendar interval starts. So for example, if you were rounding to the year, the resulting rounded values would all be on January 1st at 0 hours, 0 minutes, and 0 seconds, because that's the first moment of each new year. Likewise, if you were rounding to the hour, the resulting values would all be at 0 minutes and 0 seconds, because that's the first moment of a new hour. There's three different date rounding functions. How do each of them work? Imagine time as a continuum. Here I have three values that I'll use as reference: December 31st, 2018, January 1st, 2019, and January 2nd, 2019. Each point is at 0 hours, 0 minutes, and 0 seconds. And let's say I have an observation that's somewhere between January 1st, 2019 and January 2nd, 2019. The round date function is going to round to the closest even value. This might be before or after the observation. Depending on exactly where the observation is, it could be rounded to January 1st or January 2nd. The floor date function rounds to the largest even value before the observation. So it's going to look at times that are before the observation and find the largest even value. In this case, the observation would be rounded down to January 1st. Ceiling date does the opposite. It moves to the smallest even value after the observation. So we'll take the observation, look at dates and times in the future, and move to the next even value. In this case, it would be January 2nd, 2019. These LubriDate functions are time zone aware, so they're always going to use the time zone and the calendar that's associated with a particular date time. There may be more complicated types of rounding that you want to do. If that's the case, you can use the format function to construct a piece of text and then convert that text back into a date time. In general, the LubriDate rounding functions will probably be sufficient for your needs, but if you need to do some kind of complicated rounding, this could be an approach for you. Let's go through some examples of using these date and time rounding functions in R. I'm just going to define a date time as May 25th, 1977 at 12:18 and 53.07 seconds in the America/New York time zone. You can see the result that I get is May 25th, 1977 at 12:18 and 53 seconds in Eastern Daylight Time. As my first example, I can round that date off to the month. You see the resulting value that I get is June 1st, 1977 in Eastern Daylight Time. June 1st is the closest even month to May 25th. Floor date will give me the largest even month prior to that date time. So here I get May 1st. Ceiling date will give me the smallest even month after that date time. So I get June 1st. These functions work with smaller units of time. Here I round to the hour. That gives me May 25th, 1977 at 12 p.m. The floor date is also May 25th, 1977 at 12 p.m. And the ceiling date is an hour later, May 25th, 1977 at 1300 hours or 1 p.m. Going back to my code, these date rounding functions may seem a little abstract so far, but they're very useful for computing summaries of your data. So in this example that I have here, what I'd like to do is compute the average daily high and low temperatures. I have hourly data, so what I can do is create a new variable called day, which rounds that hourly date time off to a particular day. I'll start by taking my weather data, piping it to a mutate verb. I'll then compute a day variable, which is the floor date of date time, and setting the unit to round to as the day. Why do I use the floor date? I would like every hour on a particular day to be associated with the day that started at 0 hours, 0 minutes, and 0 seconds that day. So floor date gives me that largest day prior to each hour. I then take that, pipe it to the group by verb, and I'm grouping on that day variable. I then pipe that to a summarize verb and compute the low temperature as the minimum temperature for each day and the high temperature as the maximum temperature for each day. Let's run that. Taking a look at the output, you can see that I have a day variable that is a date time. There is one entry for each day. The low temperature variable is the low on that day, and the high temperature variable is the high on that day. This is a very useful use case for these date rounding functions. Frequently, you'd like to compute summaries over time using time units that aren't in your data, and these date rounding functions allow you to easily compute them.